So welcome back out here at the barn. It is Christmas Day 2021, but you're probably watching this after that, so it's, I don't know, January 4th. So weary time travelers, welcome back out to the shop. I've completed my contractually obligated family time for Christmas, so now I'm out here in the shop because even though I'm in southern Indiana, it is about 68 degrees outside today. So, I'm out here in the shop working on a pressure sensor for my antique tractor dyno. My PTO dyno, about 2 years ago now. It's an M&W P350. Um, a little bit of fundamental of what it does and how it works before I get into what this pressure sensor that I'm building is. So all it is a big hydraulic pump that the PTO drives, and a big valve that puts a restriction on that hydraulic pump. And everything downstream, you've got a pressure gauge that measures the pressure, because the pressure on any pump really, especially a fixed displacement gear pump, the pressure acting back on those gears, if you know the tooth area of the pump itself, you can translate that into a pressure, or the pressure into a torque, and if you're measuring RPM, you can convert that to horsepower. So the way this dyno was made, the pressure gauge just reads out horsepower, which is it reads horsepower and pressure. So at a certain 535 PTO RPM, that's the standard PTO RPM, at least in North America, uh, you run that specific speed, load the tractor down, and read the pressure, and you read the horsepower. The problem with that is, there's at different speeds, the horsepower equation is of course a function of speed. So at different speeds, the horsepower is different, and this gauge doesn't specifically put out torque on its own. So as another complication to that, this dyno never had the tachometer as long as I've had it, so I had to put in a digital one, which is a little jumpy. So I get that 535 RPM stab point and read a horsepower, all great and well. If there's a tractor that either has a low set governor or was rated at lower than 535 PTO RPM, I think the Farmall F20 was one of them at like 480 PTO RPM maybe. But even at that, one of mine, the governor breaks over even at a lower speed than that, so it's more torque than horsepower. So there was a factory sort of slide rule wheel that was made to be able to convert pressure and change the speed and get that to a horsepower. But I was able to back calculate, figure out the tooth area of the pump just based on the pressure versus horsepower graduations, and turn that back into a torque. So now that I can I know the pump equation and can read the torque, I'm thinking I want to digitize this. So this is something that's been, I think it's going to be a fun project, just because it's going to put together the really old technology of this hydraulic pump dynamometer and a Raspberry Pi to log and display the data in real time. So I've been thinking about how to do that, and I am an all hands-on guy. So the programming part, that might not even go on video. That's not gonna go very well, and that's gonna take a while. But the mechanical part, that's easy. So in order to feed a microcomputer, Raspberry Pi in my case, data. I need to be able to measure the two things that I really care about, which are the RPM of the shaft, that's an easy one, and the pressure in the system. That's a harder one. That's an expensiver one. I don't know if, I doubt any of you have ever priced pressure transducers. Don't do it. Don't price them. So I decided for fairly cheap, I could build basically a pressure transducer, because all I need is, knowing that pressure is a force over an area, I need to measure the force with this S-type load cell and then provide an area downstream. So after I do some machining, via this piston and cylinder, I can apply the pressure over the area and read it out as a load. But now I gotta stick these things together. That's better. Yeah, that's what it's, yeah, I remember now. So the idea here is I've got this load cell that is positioned with a threaded rod, actually these are carriage bolts, holding it between these two plates, basically. On the end of one plate is a little hydraulic cylinder. You can probably barely see that little piston in there. So this will get some more seal work. There's some pipe threads back here that'll plumb in. That piston will push down on the load cell, and these two carriage bolts will react it through this bottom plate of 1018. Yeah, probably. So all I've done is made this little cylinder and piston. The piston's got an O-ring groove in it, and I'm thinking I might have to put a leakage port in here just to help dampen the pressure pulsations. I'm not sure yet. Drilled a couple holes in it, made basically a flange base so that I put this piston in here, and then this load cell is, and then those are honed to fit together, so that's really a nice close fit. I took both of these M12, I think they were, bolts, and put this 90-degree tip in them because I didn't feel like indexing the compound. And now each of them have this 90-degree tip that fits each side. The piston and the base, the piston and base, have a drill center for that to fit in, so that that can align itself without putting a out-of-axis stress on the load cell, which might make inaccurate results. So I put this thing back together, and then we will do a little bit of plumbing and maybe do a little grease gun test. Okay. After looking, I don't have the right fittings, so you're just gonna have to trust me that this works until I get to the next videos putting together this entire graphical user interface and plumbing and all that fun. Oh, and doing something about these bolt heads probably, and yeah. So just another piece. I chose to make this a 1/2-inch cylinder, mostly because I had that size of reamer and pilot drill on hand, and also because I had chosen this load cell, which is a 200 kilogram capable load cell. That's twice as much as I thought. And if I remember the calculations I ran 4 months ago correctly, it said that this 1/2-inch cylinder, which math, if I remember right, it's going to be like a 250 pound force load, so even 200 kilograms would be 440 pounds. That's not a lot for 2 1/4-inch bolts, so hopefully this will work out and get it all sealed up and get it ready to go.